Industrial plants need steam for heating and other processes. Boilers are commonly used to provide this steam. You may be called on to operate the boilers in your plant. The first step towards safe and productive operation of boilers is a good working knowledge of boiler fundamentals. The function of boilers is to produce steam. Steam is produced by heating water to its boiling point. When water reaches its boiling point, it changes from a liquid to a vapor. It's this vapor that we call steam. So basically, to produce steam, you need two things: water and heat. To generate the production, boilers rely on the process of combustion. That is, they burn fuel to provide the heat required. In simple terms, there are four requirements for combustion, which we'll illustrate on a combustion triangle. One requirement is fuel. Most boilers burn oil, natural gas, or coal. The second requirement is air. More specifically, air contains the oxygen needed for combustion. The third requirement is heat. Heat is required to raise the temperature of the fuel-air mixture to a point where a chemical reaction or ignition takes place. The chemical reaction is the fourth requirement. If any one of the requirements is missing, combustion will not occur. The two requirements for steam production are water and heat. The heat's provided by combustion. Boilers are designed to allow the requirements for steam production and combustion to come together. Let's see how by looking at a boiler's basic operating principles. We'll assemble a simplified boiler. This is a container or shell. With water in it, the water takes care of one of the requirements for steam. We'll also add a pipe to provide a continuous supply of fuel to the combustion area, that is, the area beneath the shell. Heat from the flame satisfies the second requirement for steam production. As the shell heats up, heat is transferred from the shell to the water, and the water boils, producing steam. But a boiler modeled on this example won't work for industrial applications. First of all, the shell is open to the atmosphere, so there's no way to collect the steam. In addition, as the water boils to steam, there's no way to replenish it. Without water, the shell could overheat and be damaged. Given these factors, we'll have to make some changes. First, we'll cover the shell to prevent the steam from escaping. Then we'll add a steam outlet line to collect the steam and route it to where it can be used. We also need a way to supply water to the shell so it won't boil dry. So we'll add a feed water line. It will provide a continuous supply of water to replace the water that's changed to steam. Now we have a boiler that can heat water, produce steam, and route it out of the shell to where it's required. But this design is still not as efficient as it could be. Can you think of a reason why not? With this design, much of the heat in the combustion area escapes to the atmosphere. This heat is wasted because it doesn't go toward the production of steam. This boiler can be modified further to make it more efficient. By adding an insulated casing, we can minimize the heat loss, but this creates another problem. The flame goes out because the casing cuts off the source of air. To correct this, we'll add a fan to supply air to the boiler and an outlet to remove combustion gases. Although this design is still greatly simplified, now we at least have a boiler that provides a constant supply of steam efficiently. In this topic, we saw the basic requirements for steam production and combustion. We also put together a simple boiler that operates to meet these requirements and produce steam. Let's take a minute now to try some practice questions. Heat transfer is a natural process that occurs anytime there's a difference in temperature. Heat naturally transfers from a hotter object to a colder object. Basically, heat transfer occurs in three ways: radiation, convection, and conduction. Radiation is a process in which heat is transferred through electromagnetic waves. All matter gives off some radiant energy in the form of electromagnetic waves. But the best example is probably the sun. It gives off vast amounts of radiant energy. As the sun's radiant energy travels through space, some of the electromagnetic waves contact the Earth. Some of these waves are reflected back into space, but others are absorbed by the Earth. Only the waves that travel in a direct line of sight between the Earth and the Sun come into contact with the Earth. The energy contained in the waves is absorbed by the Earth as heat that warms the Earth. The amount of heat transferred depends on the number of electromagnetic waves absorbed. A second type of heat transfer is convection. Convection is the transfer of heat within a fluid, that is, a liquid or a gas. It's caused by a mixing action within the fluid. To demonstrate convection, we filled a beaker with water and set it on a hot plate. We'll also add some dye to show the mixing action. As the bottom of the beaker heats up, the temperature of the water closest to the bottom increases. As the temperature increases, the water becomes lighter or less dense, so it flows upward. The warmer water mixes with the cooler water near the top of the beaker, and heat transfer occurs. This type of heat transfer is known as free or natural convection because the movement of the fluid occurs naturally. Convection heat transfer that's produced mechanically is called forced convection. Many buildings have forced convection heating systems. These systems use fans to force warm air into rooms. The warm air then mixes with the cooler air in the room, and convection heat transfer occurs. A third type of heat transfer is conduction. Conduction is the transfer of heat through a solid object or between two objects as a result of physical contact. For example, if we heat the middle of a steel rod, the end will heat up as well. The heat transfer from one end of the rod to the other is due to conduction. We've now seen the principles behind radiation, convection, and conduction. The three main types of heat transfer are radiation, convection, and conduction. Each of these types is involved in transferring heat from the burning fuel to the water in a boiler. To see how, we'll use this example. This type of boiler is called a water tube boiler, but the heat transfer principles at work apply to just about all boilers. The boiler has a series of tubes and two drums which distribute water to the tubes. The tubes form a wall around the combustion area. This is the area where heat is generated. When fuel burns in a boiler, radiant energy in the form of electromagnetic waves is produced. These waves travel through the combustion area. The waves in a direct line of sight with the tubes make contact with the outer tube surfaces, and the tubes absorb heat. This is radiant heat transfer. The burning fuel also produces combustion gases. As these hot gases pass through the boiler, they transfer heat to the tubes as well. This is convection heat transfer. As the outer surfaces of the tubes absorb heat, conduction heat transfer occurs. Heat is transferred from the outer surface to the cooler inner surface. Then heat is transferred from the inner surface to the water flowing through the tube. Convection heat transfer also occurs as the warmer water mixes with cooler water. When enough heat has been transferred to raise the water temperature to the boiling point, steam is produced. When a boiler is working properly, the heat produced by the burning fuel will be readily transferred to the water in the tubes. However, there are problems that can interfere with heat transfer. One of these problems is a condition called scale. Scale is the buildup of solid impurities on boiler components that contain water. The boiler's feed water supply may contain impurities. These impurities coat the surfaces, insulate them, and restrict their ability to transfer heat. If the surfaces can't transfer heat to the water, the tube can overheat and rupture. A heat transfer problem can also occur if the feed water supply stops for any reason. Without a continuous supply of feed water, the boiler may boil dry. With no water to remove the heat, the tube metal rapidly overheats and severe damage may result. In boilers that burn coal or oil, another problem that can affect heat transfer is the buildup of soot. Soot's created by ash and unburned fuel particles in the combustion gas. In this topic, we covered heat transfer. We looked at the major types of heat transfer, and we saw how heat transfer occurs in a boiler. We also looked at a few typical heat transfer problems. Now let's try some practice questions. Basically, fire tube boilers route hot combustion gases through metal tubes. The tubes run through a shell filled with water. Fire tube boilers vary in design, but most operate under similar principles. The combustion area for this one is here. A group of horizontal fire tubes routes combustion gases through the boiler. There's also an outlet for the gases, a feed water line, and a steam outlet line. During operation, water enters through the feed water line. The water level is maintained above the fire tubes to protect the tubes from overheating. Fuel and air enter the combustion area. The burning fuel transfers heat to the water in the shell. The hot gases flow through the fire tubes, and additional heat is transferred to the water surrounding them. Each time the gases are routed through the shell, it's called a pass. The gases pass through 2 times in this example, so it's a 2-pass boiler. The combustion gases flow out of the boiler here in this example. As the water in the boiler is heated, some of it turns to steam. The steam-water mixture is lighter than the cooler water in the boiler, so it tends to rise. Steam collects above the water level. Then it flows through the outlet and into the plant. The feed water, which is cooler and heavier than the steam-water mixture, flows to the bottom of the boiler. It's heated in the combustion area, and the cycle continues. Generally speaking, water tube boilers use tubes to route water and steam through the boiler. The combustion gases flow past the outside surfaces of the tubes. Let's examine this principle in more detail. Water tube boilers may vary in design, but most of them operate in basically the same way. This particular boiler consists of a series of water tubes and 2 drums. The drums distribute water to the tubes. The water tubes connect the drums and form a wall around the combustion area of the boiler. This is where heat is generated. Water is fed into the upper drum through a feed water inlet line. The water tubes and the lower drum are completely filled with water. The upper drum is only filled to a certain level. This provides space for steam to collect, so the upper drum is often called the steam drum. As fuel is burned in the combustion area, heat is transferred to the adjacent water tubes. The combustion gases then flow out of the boiler. Water circulates from the upper drum through the water tubes and into the lower drum. The lower drum is often referred to as the mud drum. From the lower drum, the water is distributed to the water tubes surrounding the combustion area. As the water in the tubes is heated, a steam-water mixture is produced. The steam-water mixture enters the upper drum. The steam is separated from the water and routed through the steam outlet. And in this topic, we looked at the 2 main types of boilers, fire tube boilers and water tube boilers. We saw basically how they're designed and how they operate. At this point, let's try some practice questions on fire tube and water tube boilers.